So in this next section, again, we're going to generalize this theory a little bit further. And so before I confuse you all, let's first think about what we know so far. So we know that moment of a force is just the force times a lever arm. And so taking the example of the car wrench. So if we've got some force acting on that, like so, then we'll get a moment. That moment is just going to be the force times the lever arm, the distance. So what else can we tell from that? Well, if we were to increase this force, we'd also increase the moment. So apply a bigger force, you're going to get a bigger moment. Alternatively, if you apply that same force further away, you're also going to get a bigger moment because moment is increasing with the lever arm, this D. So that's all very well, but what you'll notice is that in all the examples we've looked at so far, that force has always been at right angles to the rigid body. And so we also got this one down here. That's also a right angle down here. Okay, so the force has always been right angles to the rigid body. What we need to think about next is what if that's not the case? How does that change things? So instead of pulling, suppose we've got an example like this, instead of pulling this straight down at right angles or straight up at right angles, what would happen if we pulled it at an angle like this, or along the axis of the wheel wrench? And just intuitively, you can imagine that as the angle of that force increases, in this case, depends which angle you're talking about. If we're talking about that angle there, then as that angle increases, then the moment on this nut must be decreasing, because by the time you get to this point, there's no moment at all in that nut. You're just trying to pull it sideways. It's not going to unscrew the nut. There's another thing about the examples so far that we've done that's made things a little simpler, but that we need to now generalize. And all of these examples have used something long and thin. It's basically using a bar or a plank for the seesaw or the wrench. All of them are long and thin, but what happens, or is there anything else we need to think about if you've got some general object and you've got some forces acting? So it might be fixed at one point and you've got some forces acting at other points, and they could be acting at different angles. So what happens then? So we'll just have a look at that with a small model that I've made up, and we'll see if there's a way that we can figure out the moments for a more generalized situation. So what we've got here is I just made up a little model of a general object, so some blob, which is some plasticine and duct tape, and it's been skewered by a matchstick, so that's providing our fixity or our point of rotation. So it's fixed at that point. In translation, it can't slide, but it can rotate about that point. And we've got a couple of forces, so these are representing the forces. So let's just re-go over what we know. So suppose we had a force and we are applying it like so. Then if that force is going to try and pull this object in this direction. I've pushed my pin in too far, so it doesn't want to rotate. And so if you had a force acting downwards like that, it would want to pull that around like so. And so that's got a positive moment. It's rotating anti-clockwise, therefore that's creating a positive moment. And because it's at right angles, it's very similar to the other ones we've done so far, its lever arm is in this direction like so. So that's the lever arm of that force. Now, similarly, just what we've already talked about, if I was to move this force further away, it would then, applying the same force, is going to apply a bigger turning moment, a bigger moment on that object. Or if I took that force away and I had a smaller force at the same position, that smaller force would have a smaller turning moment on that object, so it would be harder to stop that rotation. Sorry, it'd be easier to stop that rotation with a smaller force. The first difference here, now that we're thinking about a big, wide object rather than a little bar, is what's called the principle of transmissibility. And so if we've got a force like so, the principle of transmissibility says it doesn't matter where along the line of action of that force the force acts. And so if instead of applying, so at the moment I'm applying the force at the little drawing pin, and what I'll do is I'll just draw on the line of action. So the line of action is along here like so. And that's why I've drawn my line of action on here as well. So it wouldn't matter, the object wouldn't care if the force was acting at that point, wouldn't make any difference. And so you'd still have the same lever arm. The lever arm would still be this direction here. If I moved it right back to here, principle of transmissibility says it doesn't matter where the force acts along this line, we're still going to be using the same lever arm. So where the exact, and same down here. So it doesn't matter where that force acts along its line of action, it's not going to change anything. We'd still be using the same lever arm. I made that lever arm a bit too short, so it should really go to right to that line, like so. Okay. Now let's move back to where we started from. I'm just going to rub off that line of action. Now let's have a think about what happens as we change the angle of that force. So if we imagine, if we brought this force right round this way, I'll have to also rub off that lever arm as well, I reckon, just so you can see what's going on here. So if we had the force right round here, the moment is now 0 because, and I imagine I'm pulling this, it doesn't want to rotate at all. So if I've got at right angles, very easy to rotate that object. If I turn it this way and have the line of action lined up with, just push that in a little bit, line of action lined up with a point of fixity, it now doesn't want to rotate at all. If I move to a slight angle, then it'll rotate a little bit, but it's quite hard. Right angles, it's very easy to move it around, so that must be applying a high moment. And if I came right around to here, it's now harder to rotate that object again. So that's applying a lower moment. So I have to apply a higher force. It's got a lower moment when we've got the force right round at an angle. I'm a bit long, but, and now if I line that, if that line of action again lines up with the point of rotation, it now doesn't want to rotate at all. It wants to slide this way, but it's not rotating it at all. So what we're thinking, what we're seeing here is we've got maximum moment when we've got a right angle, and that moment is reducing as that angle increases in this case, and then it's at 0 when the line of action is lined up with a point of rotation, or the other way it's also true. So maximum moment at this point, as you rotate round, the moment reduces until when you're lined up with a point of rotation, there's no moment at all. So what we have to look at here is what else is changing as this angle of the force changes. So at this point, we've got a lever arm like so. And I've kind of not told you the whole truth about the lever arm yet, because all of our examples, the force was at right angles to the rigid body, and it was a long, thin, rigid body, so it's quite easy to see. But now, if we rotate to this point, what we can see is the shortest distance between this point of fixity and the line of action is reducing. So at this point, the shortest distance, which always makes a right angle, is starting to reduce. If we come a bit further, the shortest distance to the line of action is probably around here. So it's reducing again. As we come right down, Now the line of action goes straight across that point of fixity. So the distance between this point of rotation and the line of action is now 0. And in fact, it's these lengths that are our lever arms. So when we're trying to find a lever arm, I just need to draw this so that it goes all the way to the line. Something like that. That one's about right already, and then down to 0. So in this position, our lever arm is here. In this position, our lever arm is here. It's the shortest distance from that line to the point of rotation, which is always means that there's a right angle between this line and the line of action of the force. When we come down to here, that lever arm has now reduced to 0. And it wouldn't matter, so say for this position here, this is your lever arm, it wouldn't matter if this force was here, or the principle of transmissibility says if it was here, you'd still get the same answer. Even if it was down, let me try and get it in the right place, down here, wouldn't matter. The principle of transmissibility says that no matter where you put that, where that force acts along its line of action, we're always going to use this lever arm here. And so that's why as you reduce the angle, you reduce the moment. You reduce the angle, reduce the moment, because as you reduce that angle between, I'm talking about this angle here, as you reduce that angle between the force and the point of rotation, that lever arm is also reducing. So in this position, here's your lever arm, reduce it down. In this position, here's your lever arm. In each stage, that lever arm's reducing until when the line of action is in line with the point of rotation, you've got 0 lever arm. That's why you've got 0 moment.